I like Dunkin' Donuts if I'm going to go for overpriced coffee. Well, Dunkin' Donuts is not too expensive. You just get like the, you know.
Royal flush.
All right, I will begin. I will begin. Let me begin with a word of prayer. So, once I get over here. Heavenly Father, we thank you for this day. Again, I thank you for this class, and just ask us to help us to understand what we're going over together, and just you be glorifying what we do, Lord. In your name I pray, Lord Jesus. Amen. Okay, so today I'm going to talk to you guys about, well, hopefully I'm going to talk about Gauss's awesome theorem. But it'll take us a minute to get there. And so to start with, I need to talk to you guys about an adapted frame field. And this topic is kind of, I think it's the background concept that flows through your take-home test, take-home part of the final. And like this idea of finding a frame which encodes the geometry of your object, it's a powerful idea, which I don't think most mathematicians really appreciate as deeply as perhaps we should. I certainly don't. I mean, I'm a novice at it. Dr. Kogan you talked to at NC State, she's an expert. Her whole, like a lot of her career, as I understand it, rests on a particular kind of sneaky cross-sectional idea that she developed, which if I understand correctly, it has to do with this world of ideas, all right? But anyway, so an adapted frame field on an open subset of a, and this is going to be a surface. So we're going to talk about a two-dimensional manifold, all right? Is a Euclidean frame field, and that's just fancy talk for saying the dot product. That's a fancy way of saying it's an orthonormal frame field with respect to the Euclidean metric, okay? Such that E3 of P is an element to the perp, to the tangent space for all P in O. And we'll pretty much dispose with the concept of a open subset. We pretty much just find frame fields on the totality of the surface. So I don't see that this is sophistication is terribly necessary. So this is an adapted frame field. Now, so you can prove that there's an adapted frame field on a surface if and only if the surface is orientable, which is to say that there is a non-vanishing normal vector field, right? Basically, you just make the normal vector field renormalized your E3. Now,
Remind me what a frame is.
So a frame, like a frame on R3 is just this, E1, E2, E3, vector fields, let's say on R3, such that EI dot EJ is equal to Kronecker delta IJ. So it's a set of orthonormal, pointwise orthonormal vector fields. They don't have to be constant, but they are situated such that they're always length 1 and they're always perpendicular to each other. So some nice non-trivial examples of this. Well, here's a trivial example in the notation of the book. This one. This is the this is straight up the Euclidean frame, the standard basis basically. Example 2, you might have, for instance, rho hat, phi hat, theta hat. So these are the unit vectors in direction of increasing spherical radius, polar angle, and azimuthal angle, and those form a frame field. That's the spherical coordinate frame. And I won't bore us with equations right now for that. Example 3, cylindrical coordinate frame. So you can do like r hat, theta hat, z hat, something like that. Cylindrical coordinate frame. Cylindrical coordinate frame. Now, and of course you can express those in terms of like the U1, U2, and U3 if you want. Okay, so example 1, let's look at the cylinder. X squared plus y squared equal to r squared. All right? So you can look at this. This is essentially, so the cylinder is a level surface, and as such you can just take the gradient of the defining level function, right? So like the gradient of x squared plus y squared is 2x, 2y, 0. And as such, this tells me I will make my E3 equal to, let's see here, 1 over the radius of the cylinder times x u1 plus y u2. All right? That's a unit normal to the cylinder. Now, for E, I'll let E1, oh man, excuse me, E1, I need a vector field in R3 which is perpendicular. It only involves x and y. The obvious choice here is just U3. Right? So if you think about the cylinder, you've got basically E3 points out, and E1 is like this along the cylinder, yeah? So I want an orthonormal frame. How do I get a third vector from, I've got 2, how do I get the third? You have 2 length 1 vectors in 3 dimensions. You want a third perpendicular vector, also length 1. How do you do it? The cross product, right. So we'll just take like E3 cross E1. All right, E3 cross E1, and that works out to, short calculation here, minus x over r U2 plus y over r U1. So there's your E2.
How do we know that U3 was the 1 over r?
That's the construction. You want to pick a vector field which is normal to the cylinder. How do I know the gradient is perpendicular to the level surface? Well, that's calculus. So this vector is perpendicular to the level surface of x squared plus y squared. So that's, but of course, this is nothing more than well, really here, if you really look at what we're doing in a slightly different notation, this is the cylindrical coordinate frame restricted to the cylinder. See, because E3 is really nothing more than r hat, and E2 is really nothing more than theta hat. And this, in my usual Calc 3 notation, is z hat. Now, it's technically not the cylindrical coordinate frame because the cylindrical coordinate frame is defined on all of R3, right? Whereas this is just for the cylinder. So in that sense, it's an adapted frame field. But it is straight up the restriction of the cylindrical frame field. Yeah? So obviously, if you have a coordinate system which picks up your surface as just one of the coordinates equal to a constant, then the frame field for that coordinate system will make a natural adapted frame. Like the sphere is another example. So, example 2. So, sphere, and for reasons, I'll stick with my notes. He calls it sigma. Isn't that funky? But I guess it's the radius r sphere, so that's a little bit different than our usual unit sphere. X squared plus y squared plus z squared equals to r squared, right? That's the equation of the sphere centered at the origin. So you take the gradient of that and normalize it, what you got? So taking the gradient, you know, calls this thing f. So basically just take the gradient of f, divide by the length of the gradient of f, call that thing E3. So E3 is just going to be, you know, 1 over r times x u1 plus y u2 plus z u3. And then you can make, let's see here, I'll stick with my nomenclature in the notes. I make E1. I want to make it something perpendicular length 1. So how about this? Minus yu1 plus xu2 divided by the square root of x squared plus y squared. Notice that the dot product of these two is 0 because you get, when you take the dot product of these two, you get minus xy plus xy, which gives you 0. So these are perpendicular, and they're both length 1. And then E2, same trick again, yeah? E2 is E3 cross E1. All right, and the formula, exciting, exciting formula, here it is. It is 1 over r square root of x squared plus y squared minus xz u1 minus yz u2 plus parentheses x squared plus y squared u3. And let me demystify all this. In terms of the spherical coordinate frame, what are we looking at? Oh man, goodness gracious. In terms of the usual math jargon, this is rho hat, this is theta hat, and this is phi hat. All right, and so in the sphere, right? So like rho hat, I'll draw it here. Anywhere I draw it, I'll try. So here's your rho hat, your phi hat, something like this, and the theta hat, I guess, would be something like that. Back into the, so phi hat crossed into rho, yeah. Anyway, this much is true. Rho hat cross phi hat should give you theta hat. Should I draw it? Maybe I should draw it. So at the moment I'm using these guys, phi, theta, and so like the theta hat would point like this. The phi hat would point straight down like that here. And the rho hat would point like so, radially outward. So like phi hat, rho hat rather, crossed into rho hat, crossed into phi hat, puts in the theta hat. You can see it. Well, anyway, let me stop. I don't want to teach you guys spherical coordinates today. Anyway, the point is, this is an adapted frame field on the sphere of radius r. All right. Okay, so then what? Then we can talk about What did we do? We had a frame. We talked about the coframe. We learned that the coframe and the exterior calculus on the coframe basically told us how to how to figure out the connection, not the connection, the covariant derivative, right? We could figure out the covariant derivative, the components, the numbers that we need, the functions we needed to work out the covariant derivative in a frame field were somehow built into the wedge product and the exterior derivatives of the coframe. These were Cartanzi's equations of structure that we learned, right? So we want to understand how that gets married together with the discussion of like the shape operator. That's what we're after today. So here's a theorem. Well, first of all, let me just recall the definition. Now this is a transitory definition because we're gonna replace it. But for the moment, omega ij of v was equal to the covariant derivative in the v direction of the ei, all right, dot with ej. So that was our definition of the connection coefficients omega ij, and there's a theorem that we can get from that, namely that the covariant derivative in the v direction of ei is equal to a sum j equals 1 to 3 of omega ij of v times ej. Now that's not really much of a theorem. I mean, it's really not much of a theorem at all here, honestly, guys, because if you accept that E1, E2, E3 is a basis, an orthonormal basis, this is nothing more than the expansion of this particular vector, right, over the frame E1, E2, E3. So this is the dot product of this vector with respect to j times ej. It's nothing more than like the expansion of a vector x dot x hat times x hat, v dot x hat times x hat. Maybe let me use ijk. V dot I times I plus V dot J times J plus V dot K times K. It's that. That's what this is. That's the theorem. So I said theorem. Maybe I'm devaluing the word theorem by calling that a theorem, but nevertheless it's called a theorem in my notes, so there it is. Now proposition. This sounds more like a thing. Proposition. See, I'm debating whether I should write things. I'll write it here. I'm going to try to fit it in here. Prop. The shape operator, S of V, is equal to omega 1,3 of V E1 plus omega 2,3 of V E2. Now there's a point dependence here that I'm suppressing. I have no regrets. So this is the formula that relates the shape operator to the connection coefficients with respect to this frame E1, E2, E3. All right, so to prove this proposition, and I think we should, we need to remember that the definition of the shape operator at V is simply minus the covariant derivative, right, in the V direction of the unit normal. Right, of the unit normal to the surface. But in this context, the unit normal is E3. So this is minus the covariant derivative of E3. All right? Which then, if you look at the theorem, this proposition is like, duh. See, because just put I equals to 3, and then what do we got? We've got you know, the sum j equals 1 to 3 of omega 3j ej. And that was a v, right? But remember we proved that omega like 3, 3 is 0. Omega 1, 1 is 0. Omega 2, 2 is 0. Omega 3, 3 is 0. That's still true here, right? Because that followed from the like with the product rules for the covariant derivative. And as such, we just have omega 3, 1 of v E1 plus omega 3, 2 of v E2. But remember, omega is antisymmetric. So this is literally, whoa, dudes. Oh, omega 1, 3 of v E1 plus omega 2, 3 of v E2. Done. What is missing from my current derivation is a minus. Where does it belong? Right. Yeah, exactly. I dropped this minus. It's here and it's here, which means it's also here, right? But then I'm using that, oh man, omega ij is equal to minus omega. Maybe there's still hope for me in missing graduation. Omega ij is equal to minus omega ji. We absorb the minus. Okay? So there you go. Here's a formula for the shape operator in terms of the connection coefficients in this adapted frame. All right, then what? Well, well, well. What is next? So let me just kind of set the stage here. We have, now we have E1, E2, E3 adapted to M, right? And what that means, among other things, is that E1 and E2 are tangent to M, all right? I mean, this is what the definition of adapted means for us, okay? It means E1 and E2 are tangent, and E3 is normal, all right? And so these give you coframe theta 1 and theta 2. These are one forms on M, right? On the other hand, we have the covector, one form if you like, omega 3, which is identically 0 on M. Right? And so if you're a purist, you might be like, this doesn't really quite make sense, because if you really, well, if we had been more careful and methodical, we would have done things about a frame on an open subset of R3. And you might say, well, the surface is not an open subspace of R3. But if you want to get an open set of R3 which has all the information of the surface and not much more, what you do is you form a ribbon. You just basically grow the surface normally and just make what's called a ribbon. And then you can have an open subset of R3, which contains the surface and a little bit more, and then all of your theorems about open subsets of R3 hold, and you can get stuff. This is done in Shlomo Sternberg's book on these things. It's a little Dover book. I think I've lost my copy of it. I need to find it again. All right, so what the story is, I mean, what's the exterior calculus on M? Like, what's going on? So if you think about M, the surface, what you got to play with? You've got E1, E2. You know, these are smooth vector fields on M, right? You've got theta 1, theta 2. These are, you know, one forms on M. And then all you got pretty much is you got omega 1 wedge omega 2 times a function, right? That's your two form. And that's in addition, the smooth functions on the manifold, that's pretty much the surface. That's pretty much all you got to work with in terms of, oh, that was sad. in terms of the calculus on the surface, right? So all of this grand mess of summations and permutations and all that stuff, it all falls to like, two things. You know, there's the exterior calculus on the surface is 2 to the 2. It's got 4 basic objects in it: functions, a 1 form, there's another 1 form, and there's a 2 form. If you think about fixing a point, it's a four-dimensional space. That's it. Okay, so so we've seen right here this formula already that the omega 1,3 and omega 2,3 describe how the shape operator works on the surface, and we will soon see that omega 1,2 actually shows us how. Well, maybe you can already see it here. What does omega 1,2 tell you? We can say here already, right? This basically tells me that omega 1,2 shows how E1 turns into the E2 direction, right? Or vice versa, yeah. So there's that. Now, all right, so the let's see. Oh, I shouldn't have erased my example 1. Give me a second, guys. Well, I have no intention of working through all the calculus that supports this, but example 3, dual to cylindrical frame. So I guess I use my snazzy Calc 3 formulas if you guys don't mind. So like E. What was E1? What was E2? What was E3?
E1 was U3.
E1 was U3, okay.
E2 was negative x over r U2 plus y over r U1. E3 was 1 over r x U1 plus y U2.
All right. Now, in terms of my typical Calc 3 notation for that, we're just talking about z hat, I mean, I guess I can do this. This is actually partial z. This is actually 1 over r, partial theta. And this is, in fact, partial r, I believe, with respect to the usual cylindrical r. If you change, you can work out the chain rule here and get that. So those are helpful to understand what I'm about to write. Like the dual to the cylindrical frame is theta 1, theta 2, theta 3, what? So dual to this, dr. Dual to theta 2, rd theta. Dual to theta 1, dz. Right? So the cylinder, what is the cylinder? In cylindrical coordinates, the cylinder is just r, which, square root of x squared plus y squared, right? But that's equal to big R, right? So as you can see, the theta 3 is identically 0 on there, right? It's automatically the case that dr is equal to 0. Why? because r is equal to, little r is equal to big R. R. So, so theta 3 is identically equal to 0. This is, on the cylinder M. On the other hand, the theta 1 and the theta 2, those are dual. Those are one forms on the cylinder. Any one form on the cylinder has to be built from a linear combination of those guys. Yeah? At a point. Example 4. Example 4. On the sphere, we had, and I'm not going to prove it, but E3, well, E1. So this is what gets a little fussy here. Golly. You can understand these silly scale factors if you draw the right picture. I'm going to erase all this because we're not going to need that. So if you can't remember how to, well, some things are easy. All right, so like, in terms of like remembering things, it's rho hat, right? So as a differential operator, that is just partial rho, all right? And so if you look at this, right, and you think about sweeping a little like this or sweeping a little like that, this distance down here, so this distance is rho. This distance down here is rho sine phi, actually. So like d theta, well, ds with theta, just varying theta, it's something like rho sine phi d theta. And the ds, if you're just varying phi a little bit, is just rho d phi. And of course, the ds, if you're just varying rho, is just d rho, right? Like I don't even need to draw the picture. I'll just write the formula. ds rho in this notation is just d rho, right? If you think about just going a little bit, changing along a displacement, just varying the spherical radius. These scale factors are what you end up having to divide by for over here. So like you end up with, you need a, what was E1? Oh, I've erased it. What was the last one I wrote? E2. E2 was phi hat. So E2 was phi hat. First one was theta hat. So in my current nomenclature, phi hat should just be 1 over rho, 1 over rho, partial phi, and the theta hat's the funky one, 1 over rho sine phi, partial theta. All right. Now this, so the coframe, the coframe dual to this is what? Theta 1 rho sine phi d theta. The one that's dual to this, theta 2, is just rho d phi, and this one's easier. Theta 3 is equal to d rho. This is spherical coframe on R3. This can be adapted to a sphere. So it adapts to a sphere real nice and easy. The equation of the sphere is simply rho equals to r, right? And you literally just shove that into there. And out pops your, you've got theta 1 is r sine phi d theta, and your theta 2 is r d phi, and your theta 3 is identically equal to 0 on, on your sphere. Okay? And there's just 1-2 form up to a constant multiple, right? Theta 1 wedge theta 2 is in fact r squared sine phi d theta wedge d phi. All right? All right, cool. So what are Cartan structure equations adapted? I guess I'll have to do that over here. We don't actually need this anymore, do we? Right? Okay. So it was actually shockingly easy to derive the Cartan structure equations using the attitude matrix calculus, right? Like that derivation to me, it was really one of the more fascinating calculations in this whole story arc. But here is the Cartan structure equations. Adapted to M. All right. And so we have E1, E2, E3, adapted frame on M, subset of R3, just to recap, with dual forms theta 1, theta 2 on M, all right, and then the connection forms omega ij satisfy the following. Number one, d theta 1 is equal to omega 1, 2 wedge theta 2. D theta 2 is equal to omega 2, 1 wedge theta 1. And then up number next, omega 3, 1 wedge theta 1 plus omega 3, 2 wedge theta 2. It'd be 0. So just to give you some names here, what is math without name calling, you know? So this is the first structural equation. First structural equation. This is sometimes called the symmetry equation. All of these together, they're just stemming from looking at the thing we worked out before, which was d theta is equal to omega wedge theta. Where remember our theta was a, you know, in this wild world, the theta was equal to, remember, theta 1, theta 2, theta 3, etc. So if you look at that, this is the first component of this equation is that. The second component of that equation is that. And the third component of that equation is this, because d theta 3 is identically 0. So it just leaves you with the wedge product, the third component wedge product, which is 3, 1, 1, 3, 2, 2. That's what you get in this matrix column vector wedge product. And that's it. And then the other part of the structure, the other part of Gauss Cartan structure equations involve the differential, the exterior derivative of the connection forms. And so that brings us to equation 3, known as Gauss's equation, which says that d omega 1, 2 is equal to omega 1, 3 wedge omega 3, 2. Oops, that was a 3, 2. This is Gauss's equation. And then 4, there's two things in 4. These are called the Codazzi equations, d omega 1, 3 and d omega 2, 3, which are equal to, respectively, omega 1, 2 wedge omega 2, 3 omega 2, 1, wedge omega 1, 3. So these two guys collectively are the Cauchy equations. Cauchy. And so I have some commentary here. I say that the Cauchy equations basically tell us how the shape of M changes from point to point, since the shape operator is determined by omega 1, 3 and omega 2, 3. Notice that S is fixed by omega 1, 3 and omega 2, 3, right? These equations involve omega 1, 3 and omega 2, 3, the change in those. And apparently it's related to the omega 1, 2 form, but also these guys. So this has to do with the shape operator. And I guess this one at first glance appears like it might, you know? But, well, we've got some things to learn about that. This theorem, Cartan structure theorem, there's nothing to prove here. We already derived all of these the other class for an arbitrary frame field in R3. All we have to do is take that theorem and restrict it to the surface. Basically just pull back Cartan structure equations to your surface. They're all true because the pullback preserves wedge products and differentials. Cartan structure equations are written in terms of wedge products and differentials, so it pulls back. That makes sense? So we can use these to calculate. So now we can try to use these structure equations to like calculate the connection forms on a sphere, right? Like, let's see if we can do that. Annoyingly, I haven't. Well, you guys, I'm going to write some formulas down. You guys help me interpret them. First of all, let me fix this. All right, so we've got theta 1 is equal to r d phi. Theta 2 is r sine phi d theta. Where am I?
0.
0. What am I working on? It looks like I'm working on the sphere, right?
Yeah, it should be 0.
So this is the sphere, but admittedly I have, it's not quite the same nomenclature as my example. It's like example 4, but I've flipped the script here on. I'm going to leave it. I'm not going to try to comport with that. I'm just going to. This is a different sphere, different. So the thing is, one of the annoying things about the book that we're using, well, it's not annoying. It's actually really cool. He sets up spherical coordinates so that the angle, there's an angle which is 0 on the xy plane. So you know how on the xy plane, it's like in the usual math sphericals, it's like phi equal to pi over 2. Well, in his setup, phi is equal to 0 on the xy plane. It swings up to pi over 2, and it swings down to minus pi over 2, which in some ways is much nicer. If I had to do it all over again, I think I'd use his choice on everything. But so there are at least 3 disparate uses of spherical coordinates that are popular in the literature, with counting that, the math, and the engineering. Like, you got to watch out for spherical coordinates. They're different for different folks. So I have no regrets. I'm going to stick with this. But admittedly, it is at odds with my example 4. So we will give it a new name, example 5. So anyway, it should be fairly clear that this is a coframe on a sphere. it's dual to a frame. Now, so we can calculate like what's d theta 1, what's d theta 2, what's d theta 1?
What's omega 1, 2?
No, what's the exterior derivative of this?
Nothing.
That's right, 0. We have a winner. What's the exterior derivative of this? We got what? We got r cosine phi d phi wedge d theta. There you go. Exterior differentiated. But on the other hand, we know that d theta 2 is equal to omega 2 1 wedge theta 1, right? Which tells me that, what does that tell me? That tells me omega 2 1 wedge, what was theta 1? It was r d phi, right? Is equal to what? It's equal to d theta 2, which is r cosine phi d phi wedge d theta, right? And what else do we know? We know that d theta 1 is equal to omega 1 2 wedge theta 2, which tells me that omega 1 2 wedge r sine phi d theta is equal to what? 0. Excuse me, guys. So you look at this, and you look at that. Let me be a little bit systematic about this. Omega 1 2 is equal to something times theta 1, right? Oh, well, okay, fine. Yeah, it's something plus something else times theta 2, right? Maybe I should have, see if I was smarter, I probably should have just left that as theta 1. I should probably left that as theta 2. So my point to you guys is like omega 1 2 wedge theta 1 is actually equal to what? B, right? Times theta 2 wedge theta 1. And omega 1 2, well, let's say omega 2 1. Rats, I chose the wrong number in. Because I'm trying to look at this one here, right? So I want omega 2 1 wedge theta 1. So I should have, son of a gun. That puts a minus here. All right. And then this one, omega 1 2 wedge theta 2, what's that give me? If you wedge theta 2 with this, that's 0, and it just leaves you with a theta 1 wedge theta 2, right? But what are those? That's minus b. What's theta 1 wedge theta 2? We worked it out over, oh, careful. Let's work it out. Careful, careful. No drinking from example 4. Poison. It's reverse poison. Anyway, so theta 1 wedge theta 2 wedge theta 1 r squared sine phi 2 wedge 1. So d theta wedge d phi. And this would be a r squared sine phi what? Theta 1 d phi wedge d theta, right? But we also know that those are equal to what? They're equal to the differential of theta 2, which is this, right? So this is equal to r cosine phi d phi wedge d theta, and this is equal to 0, right? So if you look at all this, you can figure out what A and B have to be by process of elimination, right? Like, what does this tell us? Is r squared sine phi d phi wedge d theta, is that equal to 0? Is that equal to 0 on the sphere? It is not. Not usually. Not everywhere at least. So this makes A equals to 0. On the other hand, this equation up here, you notice that these got to be flip-flopped, right? To compare this directly, you got to anti-symmetry, pull the minus. And so this tells me what? How did I get a sine phi? Oh man. Oh, I'm confused.
A2.
Oh man. Theta 2. Yeah, maybe it's fine. Maybe I just need to keep going.
5.
What does this say B is equal to? What's this tell us B is equal to? Fine, let me just write. So we've got minus B r squared sine phi is equal to r cosine phi, right? So apparently B, and the minus is gone.
Yeah.
So apparently B is equal to what? R cosine phi divided by r squared sine phi, if I haven't done something stupid, which is debatable. And so that makes my omega 1, 2 equal to B theta 2 theta 2, and what was theta 2? Theta 2 was r sine phi d theta, which just gives us r cosine phi. Oh, the r's cancel.
Get rid of all the r's.
So we just get what? We just get cosine phi. They be canceling? I like the way you think. D theta. Yeah. Hey, that's what I have in the notes. All right, finally, we saw our way through it. Yes, yippee. My point to you guys is you can use Cartan structure equations to calculate the curvature, not the curvature, the omega 1, 2 here at the moment. Let me move along. So, next up, I will foolishly erase this. Oh man. All right. There's still hope. There's still hope. Let's see here. So, lemma. Lemma 2.2. It says that omega 1, 3 wedge omega 2, 3 is equal to the Gaussian curvature times theta 1 wedge theta 2. And that's number 1. Number 2, we got ourselves omega 1, 3 wedge theta 2 plus theta 1 wedge omega 2, 3 is equal to 2 times the mean curvature, theta 1 wedge theta 2. So essentially all of these formulas follow immediately from the proposition. So the proposition, you will recall, told us that S of V equal to omega 1,3 of V E1 plus omega 2,3 of V E2. So then, if we look at the matrix of the shape operator in the adapted frame, what's it look like? So the matrix of the shape operator in the adapted frame looks like what? So we need to look at like what's oh man, mine just went blank. Yeah, so we can work it out, and the matrix in the adapted frame looks like this: omega 1,3 E1, omega 2,3 E1, omega 1,3 E2, omega 2,3 E2. All right. So that's not terribly complicated. So to find the matrix of a linear transformation with respect to a basis, you look at the coordinates, right, of the first basis element as your first column. So here we're using the basis E1, E2. So E1 is both places. The coordinates of S of E1 are this and that. The coordinates of E2 are this and that. But remember that the curvature is the determinant of the shape operator. And the mean curvature is the trace of the shape operator. All right. Now, past this, I guess I'll need to delete my spherical basis under there. But so it's just as well. I'm going to inadvertently mix this with the other example, and then I will get really confused. My apologies for using two different choices of spherical coordinates today. Not awesome. I mean, two different adapted frames to the sphere is what I really mean to say. So look, guys, the proof of the lemma, I don't want to write it out. I just want to think through it with you guys. So omega 1,3 wedge omega 2,3. I guess I have to write something out. Drat. So omega 1,3. I think it's that. Oh, it's the. What is it? Curses. So omega 1,3 is equal to what? It's equal to omega 1,3 of E1 theta 1 plus omega 1,3 of E2 theta 2. And likewise, omega 2,3 is equal to omega 2,3 of E1 theta 1 plus omega 2,3 of E2 theta 2. Why is that? I'm doing nothing more than expanding one forms in the basis of the one forms, namely theta 1 and theta 2. How do you find the components with respect to the basis? You operate the one form on the